Hello, in this video I'm going to talk about the photoelectric effect, and it was Einstein's explanation of the photoelectric effect that was a major step forward in the foundation of quantum physics and the transition from classical physics to modern physics that happened in the early part of the 20th century. But before I get on to what Einstein had to say about this and why that was so important, I'm just going to run through what the photoelectric effect is. So this is where we've got a metal surface, and of course there's lots of free electrons inside the metal, and we're particularly interested in the electrons at the surface of this metal. We then shine some electromagnetic radiation upon the surface of the metal, and this in some circumstances can cause electrons to be emitted from the surface of the metal, and these electrons are then referred to as photoelectrons. Now, the circumstances to make this happen will depend upon the metal and the radiation. So usually we're looking at UV radiation. You can get this to happen, this effect to occur with visible light in some circumstances, like if you're using sodium and you've got light which is towards the blue end of the visible spectrum, then it can be observed, the photoelectric effect. You can go to higher energy electromagnetic waves as well. I mean, you can get the photoelectric effect with X-rays, but X-rays also do a lot of other things. So the effect is perhaps most pronounced with UV radiation. But this is what we're talking about here: incident EM radiation upon a metal surface and then electrons being emitted. And this was first observed in the 1880s. So Hertz was looking at sparking between metal surfaces. So you've got a couple of metal surfaces, a spark going from one surface to the other. So that's electrons jumping from one surface to the other. And he noticed that this sparking happened more readily if he shone UV radiation on the surface of the metal. So this was, giving a helping hand to these electrons to make the jump from one surface to the other. So Hertz observed this. In 1888, we then had the first time the gold leaf electroscope experiment was conducted. And this is something which comes up quite a lot in exam questions, actually. So the gold leaf electroscope, this is where we've got our metal plate. So say we've got a zinc plate, and then off of this plate you have a spike going down, another zinc spike going down into a tube, an evacuated tube. So we've got this T-shaped structure here of zinc, and with one bit of it in a tube. Down the bottom of the tube you put a gold leaf, so a bit of gold foil essentially, at the bottom of the spike, and it's just attached at one point. So this other end is free to move. So it's like a thin bit of gold foil which can just move away from the zinc spike or back towards the zinc spike. And the thing that's causing this gold leaf to move is the charge on the system. So if we charge up this metal construct that we've got here, so we touch a negative terminal of a power supply or negative plate of a capacitor or whatever, something negative to this top plate, then we charge up the top plate with negative charge, and this charge will spread around the system. So you get negative charge going all the way down the spike that's going into the tube, and then negative charge onto the gold leaf. The electrostatic repulsion then between the gold leaf and the spike causes the gold leaf to move outwards. So it moves from, if that's your spike initially with a gold leaf just hanging straight down, the gold leaf now moves out, so it's sticking out at an angle. And you can see this, it's large enough to just look at this with your eyes and see this gold leaf move outwards because we've got all this negative charge. Then we set off the photoelectric effect. We get some UV radiation, we shine it at the zinc plate at the top, this top plate. Photoelectrons get emitted, which means this negative charge is being lost throughout the system, and the gold leaf then falls back down to hang straight down again. So we're demonstrating that by shining UV radiation onto the metal surface, we can cause negative charge, i.e. the electrons, to leave the surface. So that's a demonstration that the photoelectric effect exists. but it doesn't explain what's actually going on. And this is where Einstein stepped in, because people were having trouble with this. They had classical wave theory at the time, and you said, okay, well, clearly we've got some energy coming in. So we've got energy in from the UV radiation, and we got energy out in the electrons. And the energy out then must be some amount of energy to release the electron from the metal, and then whatever's left over is going to go to kinetic energy of the electron. Now, from wave theory, from our classical waves, and we looked at all of this, well, quite a while ago now, but the energy is to do with the intensity of the wave, and the intensity is to do with the amplitude of the wave, because that was proportional to the amplitude squared. So that's telling us one thing about the energy of the wave. And then the amount of energy that's going to get absorbed by the metal surface is going to depend upon the intensity and the amount of time that we're shining the radiation on the surface. So we're expecting, if we're looking at classical physics, for the energy to be a function of intensity and time. That's what we're expecting. When we conduct experiments using photoelectric effect, this is not what we see. We see something different. And there are a number of things which are a problem for classical physics in this. So first of all, we get that emission only occurs if the frequency of the radiation, so this is something which hasn't even been considered from the classical point of view, the frequency has to be greater than some threshold frequency, which I'll denote with an F subscript 0. If we're not at a higher frequency than the threshold frequency, then we don't get any photo emission at all. No matter how strong, how intense the light is and how long we're shining it for, nothing's getting emitted. So that's already a problem, because we'd think with this, well, okay, well, we just keep on, it might be low frequency, but if we just shine it for long enough, eventually, surely we're going to get some emission of photoelectrons. But no, we don't. The observations are to the contrary. And these threshold frequencies, for zinc, it's somewhere in the UV. For sodium, then you're looking, I think it's yellow light. So if you've got something shorter wavelength than yellow, then you can get photo emission. But sodium's not great for building electroscopes and things because it's so soft, isn't it, as a metal. So yeah, you want something in the UV or thereabouts just to get things going there. So that's first thing. Then we get emission is instantaneous if you are above the if you're above the threshold frequency, then you get instantaneous emission. So again, this is going against what we were expecting in classical wave theory. It's taken this time part of it out of what we were expecting and what we're actually observing. So there's another problem. Then we've got the rate of emission. So rate of emission is essentially the number of photoelectrons. So the number of photoelectrons is proportional to the intensity. So we're seeing here that the number of electrons proportional to intensity, not the energy of the electrons being proportional to the intensity, because we're also seeing that if you increase the intensity of the incoming radiation, the kinetic energy of the electrons doesn't change. There is no relationship there between intensity and kinetic energy. What you're getting from the intensity increasing is more electrons emitted. So again, another problem. We've kicked both the T and the I into touch here from our expectations. What is actually increasing the kinetic energy of these electrons is increasing the frequency. So if you increase the frequency, then the kinetic energy of the electrons goes up. So we've got a whole load, we've got 5 observations here, which are contrary to what people were expecting at the time. And this is where Einstein stepped in, and he extended Planck's idea of radiation as being quanta of energy. So I spoke about this in the last video. Planck was describing black body radiation, and he used this idea that the radiation was actually quantized, that you're getting packets of energy. And these packets of energy, each one has got an amount of energy equal to h times f, the Planck constant multiplied by the frequency of the radiation. So Planck had used that to describe black body radiation. Now, he wasn't entirely convinced that this was a real phenomenon, that this was actually describing something in the real world. He was happy it was a mathematical trick to actually explain the observations of black body radiation. But people were, this idea was out and about. People were kicking it around, and Einstein used this then to explain what was going on in the photoelectric effect. So he then said, well, what if this incident radiation, this UV radiation, is actually just a whole stream of photons coming in? So these photons are coming in, and each one of them has got energy HF. So if you increase the frequency of the radiation, so this is the frequency of the radiation, not the frequency that the photons are arriving at. It's the frequency of the actual radiation, the frequency of the wave, because we're getting into wave particle duality here that we're seeing in quantum physics. So the frequency of this wave, if you increase that, then each one of these photons will have more energy. So that then explains this. You increase the frequency, you increase the kinetic energy of the emitted electrons. Because Einstein was saying, well, these photons that are coming in, you get a one-to-one interaction, photon to electron. And these electrons will either result in reflection, as in the photon will just bounce off and all of the energy is taken away, or the energy of the photon will be entirely transferred to the electron. In which case, one-to-one interaction, if you increase the intensity of the incoming radiation, that means you're getting more photons. So that explains this one here. Increase the intensity, you're getting more photons, you're getting more one-to-one interactions, so you're getting more photoelectrons, which is what we've seen in this third observation. So that's explained both of these. It also explains why we don't get an increase in kinetic energy in this fourth observation when we increase the intensity. Because, okay, we might have loads more photons coming in, but each photon has got a fixed amount of energy. The energy is quantized. So each photon has got energy HF, and that is a one-to-one interaction with the electrons. So it doesn't change the energy of the photoelectrons. Also explains here why emission is instantaneous. These photons can just turn up straight away. You flick the light on, the UV light on, and a photon then appears at the surface of the metal. It's immediate. We don't need a time build-up. We don't need an amount of wave to have been incident upon the surface in order to get the energy that we need. We don't have this time part of the incoming energy anymore. If a photon arrives, it arrives with a packet of energy. And if that packet of energy is enough to release the electron, then great. It just instantaneously gets emitted. So it explains that. And then that touches then on the first observation. We need a minimum amount of energy to release the electron from the surface. So that means we need to have a minimum photon energy, which means we need a minimum frequency. So Einstein put all of this together to explain all 5 of these observations, and then he set up, off of the back of this, the photoelectric equation. So the energy of a photon, h times f, that's our packet of energy, our quantum of energy that's coming in. That is then, so that's our incoming energy. This is just a conservation of energy equation. Incoming energy on the left, outgoing energy. We've got the work function, which we denote with this Greek letter phi. So the work function, this is the minimum energy required. And it's important that this is the minimum energy required for release of an electron from the surface. So that's our work function. And this varies from metal to metal. We can see here for zinc, the fact that you need UV means the work function you're going to have is going to be greater than for sodium when it's yellow. This needs more energy in UV than sodium does in yellow. So the work function depends upon the metal. That is our minimum energy for release. What is left over is then the kinetic energy of the emitted electron, the photoelectron, but that will then be the maximum kinetic energy because we got the minimum energy for release here. Now, most photoelectrons are going to require more energy than the work function in order to be released from the surface. So they're going to have kinetic energy, which is less than the maximum. So you can just see this is a conservation of energy equation here. Energy in is equal to energy out. And all of this is explained by having light, electromagnetic radiation, as being a beam of photons, each photon of the same energy. So Einstein put all of this together, and we get a lot of questions. Yeah, this is an easy equation to use, simple maths, and we can also draw a lot of graphs off of these. This is a y equals mx plus c type affair, isn't it? Particularly quite often we'll write it out as a ke max is equal to hf minus phi. So we've got y equals mx plus c. So if we're plotting this sort of thing out, you can do a whole load of measurements. You're going to get something which is looking a bit like this. So we've got our intercept here is going to be our work function, and we're going to get our gradient is going to be our Planck constant. So there's two things we can work out off of this, that we've got both the work function for a particular metal, and then once we know that, we can also work out from the gradient what the Planck constant is. So it's a particularly useful equation. But this has completely revolutionized everything that's going on in physics, because now we can only explain this effect by using this wave particle duality of electromagnetic radiation. We need to describe this incoming radiation as particles, as photons, with quantized energy. So it really is completely different to classical physics. So what I'm going to round off with then on this is then Millikan's verification of Einstein's equation, because Millikan, so the same guys who did the oil drop experiment when we were looking at the quantization of charge on an electron, and he did another experiment to verify Einstein's equation. So what we've got in this is quite a tricky picture to draw out, but it's useful to do it bit by bit. We've got like this central turntable inside an evacuated tube, but I'll draw the tube on in the middle in a minute. So we've got this turntable, so it's rotating around, and we might have, say, let's have 3 bits of different metal stuck on this. These are the metals that we're going to be shining the radiation on. So we might have some sodium, some lithium, some potassium, something like that. So we've got these on here. So these can rotate round, and we need to keep these surfaces clean, because the trouble is, if you've got any impurities, so whether it's dirt on the surface or whether the surfaces have oxidized, these are quite reactive metals, so they oxidize in air, and then the photoelectric effect doesn't work, because we're not just shining the light straight onto a metal surface, we're shining it onto an oxidized metal surface. So we need to keep these surfaces clean. So set up like a knife structure, like a blade over here. So as you turn this thing round, the metals then cut across this knife, and it just slices the top off of the surface of the metal, keeping it clean. You're always removing the oxidized part of the metal. And we try to reduce the oxidation anyway by putting all of this inside a vacuum tube. So all of this we're going to enclose in some kind of vacuum structure. That can go off to your pump. So we got all of this hidden away. And then, so it's already looking a mess, this diagram. But still, we've got then, we hook this up to an electrical circuit. So I'll do this in a different color. So this can then go off to some kind of variable power supply, and we can have, let's stick an ammeter in, and then this can go off to earth over here. So when we're getting, and we have a big, let's have some kind of metal plate here, which I'll put a gap in so we can actually shine in the radiation. But if you've got a setup like this and we shine the radiation in, So we got some monochromatic light coming in, so we know what the frequency is. We shine this upon the surface of the metal. Now, without all of this circuitry going on, of course, what's going to happen? We shine the light in, bit of UV on the surface. We're going to get these electrons. The electrons have got some kinetic energy, so they're going to zap off to this metal plate here, this blue metal plate that I've drawn around this end of the tube. And they're going to cause a little current. We're going to get a current in the ammeter as these electrons then shoot off to Earth. They're going to be attracted to this zero potential point down here. So they're going to shoot off down there. If we then crank up the power supply, we can then, if we put positive here and negative here, now we're repelling these electrons from this plate that they're being collected by. So we're slowing them down. So we're reducing the current. We're going to start off at some maximum current, and then we're going to slowly increase our EMF here, slowly increase that up. The current is going to be dropping down until eventually we're going to stop these electrons. They're no longer, they're going to get released from the metal, but they're not going to be able, they don't have the energy to actually make the transition to this metal plate and then go down through the ammeter to Earth. So we're going to reduce the current down to 0 amps. This is what we're doing. We've then got our stopping potential. When we've got 0 amps, we've got some stopping PD. And that is going to tell us about the maximum kinetic energy of these electrons that are being emitted. Because our stopping potential means we've got E times V. That's how much energy they would have to have in order to overcome this potential difference between the metal surface and the metal plate that they're trying to reach. So that is our stopping potential. E times V is the energy required to overcome it. And that is going to be equal to our KE max, which is equal to our HF minus work function. So we're connecting Einstein's photoelectric equation with this stopping potential by hooking it all up to this circuit. If we then divide through by the charge on the electron, we then get this stopping potential is going to be equal to HF over E minus the work function over E. We can then, we can plot this out. Again, we've got another y equals mx plus c set up here. So we've got a y equals mx plus c, which means we can repeat this for different frequencies, for different metals. So we're changing around, different values for f and phi. We can repeat this loads of times, plot it out, and then use the intercept and the gradient to get both Planck's constant and the work function of these different metals. So it's a really nice experiment from that point of view. And this is how Millikan actually verified that Einstein was talking sense. All of that explanation that Einstein put together with these photons and his quantized energy and his photoelectric equation and everything, it made sense in theory, but theories sound great, but you need to actually show that the theory works in reality. And this is what Millikan was doing with this particular experiment. So really nice, that one. So anyway, that goes through everything, at least for getting us started on the photoelectric effects. And you can just see how revolutionary this is, how it was back in the day, 100 years ago, well, over 100 years ago. Einstein was doing this in 1905 when he came up with the photoelectric equation. So we've had 120 years ago, this groundbreaking change. Wow, now we can see light, electromagnetic radiation. We can describe this as particles, these photons, this quantized energy. This is opening up all manner of doors, all manner of things that need to be investigated about why light is behaving that way, and needing a whole new comprehensive theory around the behavior of electromagnetic radiation. So groundbreaking stuff.